In order to use the evaluation theorem regularly, it's helpful to have a convenient notation for antiderivatives. Previously, we used uppercase letters to denote antiderivatives of functions, but given our notation for definite integrals, there's another notation that's commonly used for antiderivatives. The notation is given in this slide. In particular, this symbol here, which is the integral of f of x dx, when there are no limits of integration given, is traditionally used for the antiderivative of the function f, and it's called the indefinite integral. And it's important to be clear about the difference between an indefinite integral and a definite integral. An indefinite integral looks just like a definite integral, but it doesn't have any limits of integration on the integral sign. So in other words, the integral of f of x dx, when no limits of integration are given, represents the antiderivative of little f of x. So in terms of our previous notation, using uppercase f to denote an antiderivative, the integral of f of x dx is equal to capital F of x. And now again, we need to stress the difference between a definite integral and an indefinite integral. A definite integral, where limits of integration are given, is a number. It's not a function, and it doesn't depend on x, as we've seen previously. However, the indefinite integral, where we don't give any limits of integration, is a function or a family of function. It represents the antiderivative of the function lowercase f of x. Now, the connection between indefinite and definite integrals is given by the evaluation theorem, of course. Remember, the evaluation theorem says that we can compute a definite integral once we know an antiderivative of the function. While using an indefinite integral to represent the antiderivative of f of x, we can write the evaluation theorem as follows. The integral of f of x from a to b is equal to the indefinite integral evaluated at b minus the indefinite integral evaluated at a. This is nothing more than what we had before. It's the antiderivative of the function little f of x evaluated at b minus the antiderivative of the function little f of x evaluated at a. Only now we're using our new notation in terms of indefinite integrals. The other thing to stress is that whenever we're looking for an antiderivative or an indefinite integral of a function, and we come up with something that we think is the right answer, it's always possible to verify our answer by differentiation. We take what we think is our antiderivative or our indefinite integral. If we differentiate it and we get our original function back, then we know we have the right answer. Now, in order to compute definite integrals using the evaluation theorem, we're going to need to have a supply of antiderivatives or indefinite integrals. And this table gives a set of antiderivatives or indefinite integrals that we will commonly use in a variety of problems. The first two lines simply give a couple of rules of indefinite integrals. The integral of f of x plus g of x is equal to the integral of f of x plus the integral of g of x. And likewise, if we have a constant times the function f of x, we can take that constant outside of the integration. And then we have a whole list of different indefinite integrals. And again, these are things that you should ultimately commit to memory so that you can readily compute indefinite integrals when you need to. We will focus primarily on things like the power rule here, the exponential functions, the logarithmic functions, and simple trigonometric functions like sine x and cos x. These other trigonometric functions we will typically use less often in this course.